We've been solving functions for quite some time now. Today we'll be using similar techniques that we've been using in the past to solve trig equations. So just for some context, imagine we've got a linear function y equals 2x plus 2. If we wanted to find the x-intercept, we'd let the y value equal 0. 0 equals 2x plus 2. This is basically asking the relationship for what value of x is y0. And when we solve it, we can find that out. So it's when x is -1. So it's exactly the same with trig functions. So up here we're solving or finding all the solutions to the equation cosine of theta equals 1/2. And this is basically asking the question, when are the y values for y equals cosine of theta equal to 1/2? And so graphically we can see this. Here's the standard cosine function. Okay, so we can see pi on 2, pi, 3 pi on 2, and 2 pi. And we can see that this red line here is the graph of y equals 1/2. So we can see that it's 1/2 there. That's when the graph is, or the equation is going to be equal to 1/2. Then it goes down, comes back up, there, there, there. And we can see here that trig functions are actually going to produce an infinite number of times where it's equal to 1/2. So first thing to note, unless you set the domain, CAS will provide what we call the general solution. That is a way to describe the infinitely many solutions that a trig function has. So see here, I've asked it to solve cosine of x equals 1/2 for x, and it gave me these two solutions here, which are called the general solutions. Okay, and you'll know you've got a general solution when you see kind of this thing here. It describes a constant, whereas here we say solve cosine of x equals 1/2 between 0 and 4 pi, and it goes, okay, I know that there's a finite number of solutions. In fact, we can see here we've got 1, 2, 3, 4, so it produces once, twice, 3, and 4 solutions. Okay, so it's important to know that for this particular exercise, what we're going to be doing is solving trig equations over a restricted domain. So let's try one here. So the first one is going to be a CAS-based question. And the reason I know that is we want to find all the values of x between 0 and 360 degrees when sine of x is equal to -0.6. Now the reason I know that we can't do this one by hand is that really this is asking the sine of what equals 6 on 10 or -3/5. And if you think to your exact values, we don't know any of these ones. So when we're talking about exact values, we know ones for √3 on 2, we know ones for 1 on √2, we know ones for √3, 1 on √3, what are the other ones? 1, 1/2, all of those are the ones that we would be expected to do by hand. These ones here, or this one here rather, we're going to be expected to do that on CAS because we don't know exact values for this one. If I said where is -3/5 on the exact values table, you go nowhere. Alright, so let's ask the question for this one. So we're in degrees mode, which is important to note. So I'm going to go sine of x, and I'm going to run a solve on that. So solve sine of x equals -0.6 for x, and I want to give a domain with 0, and I'm going to go control less than or equal, I find this really fiddly on the computer, less than or equal to x less than or equal to 360. Alright, now let's see if we can anticipate how many solutions there is going to be. So the standard sine of x function goes like this over 360 degrees or 2 pi. We're saying when is it going to equal -0.6? Now we can see we're going to get 1, 2 solutions. And we can see that the two solutions, we can see roughly where they're going to be. So here's 180 here at the halfway mark. So we can see it's going to be above 180. So I'm guessing around 320 and around 280 or something like that. Okay, I'm not 100% sure. Let's see what we get out of the calculator. So I'm going to hit enter, Whoops. Try that again. Going to hit enter. Alright, so I was a little bit off, but that's alright. So we've got two possible places. So x equals 216.2 decimal places. 869 is 87 degrees. That's the first time. And x equals 323.13 degrees. Alright, so we've got two solutions. Alright, so now the next one. Find all values of theta between 0 and 2 pi for which 2 sine theta equals negative root 3. And we notice there's no decimal place suggestion because they want the exact values, because we can do this all by hand. We don't need the calculator for this one. So this one here is no cas. Alright, so let's try this one out. So the first thing we're going to do is try to get this sine of theta by itself. So I'm going to divide both sides by 2. So I'm going to go sine of theta equals negative root 3 on 2. Now this one here should ring a bell because it's one of those exact values that we know. It's this one here, root 3 on 2. So we can do this one by hand. Okay, so the technique will go basically that what we want to do is find what we call the base or reference angle. So I call it the base angle, or here teachers calling it reference angle. It doesn't really matter what you call it. Okay, which is basically just to consider when is the sine of theta going to equal a root 3 on 2. Okay, so that's going to be when it's at pi on 3. So the sine of 60 or pi on 3 will give me a root 3 on 2. Okay, so that's our base angle. Alright, now what we want to do is note on the unit circle, when are we going to get negative root 3 on 2 for sine? Okay, and I know it's actually going to be in this quadrant here and this quadrant here. Okay, that's when we're going to get a sine value of negative root 3 on 2. So what's that going to be? Well, here's pi on 3, 2 pi on 3, 3 pi on 3. It's going to be 4 pi on 3. This is 5 pi on 3. And this is going to be 6 pi on... no, it's not. It's going to be 3 pi on 3, 4 pi on 3 right there. 5 pi on 3 there. And here we're back to 6 pi on 3 or 2 pi. Okay, so these are our two times where sine produces this negative root 3 on 2 value. Okay, so the way we're going to answer this question here is, if we're solving for theta, we're going to say it's theta equals 4 pi on 3 and 5 pi on 3. Now we can check this out in a few ways. Okay, so the first way I'm going to do it is define a function, f of x equals sine of x. Okay, I'm going to jump into radians mode. How do I swap that? Okay, I just had to pause the video to try and do it, but you should be able to just click on that and it should swap to rad, but I had to go into documents for some reason, so it's something not working on my emulator here. Anyway, beside the point. So I've defined f of x equals sine x. Now I'm going to find f of and one of my solutions. So I'm going to go 4 pi on 3. So 4 times pi on 3. Alright, so if this is correct, what the calculator should fire back is negative root 3 on 2. Let's see what happens. Hello, hello, hello. I was right. I love being right. Okay, and the next one is 5 pi on 3. This should also produce a negative root 3 on 2. And there it is. Okay, now the other way we can do this is we can run a solve. F of x equals, in this case we're trying to find out when it equals negative root 3 on 2. So we're going to go negative control root 3 on 2 for x. Now note that what we're going to get is a what do you call it? Oh my god, mental blank. Come on, Paul. It is a general solution that we're going to get unless we give a restricted domain. So it's between 0 and 2 pi. So 0, and I find this again really clumsy, less than x, less than, what was it, 2 times pi. Alright, and we can see there that on the solve it gave us the two solutions. Okay, so there we have it. All right, let's get on to the next question. Find all the values of alpha where it equals this, or this equation equals 0, and we've got a domain of negative 2 pi to 2 pi. Okay, so the way we're going to do this is we're going to rewrite this equation here. So we're going to go cosine 2 alpha equals 1 on root 2. So I've transposed it, added 1, and divided by root 2. Okay, so remember now what we're going to do is get our base or reference angle. So 1 on root 2, anything involving a root 2 is going to be a pi on 4 reference angle. Okay, so now specifically we want to know when cosine will produce a 1 on root 2. Okay, so that's our base angle. So we're going to get a 1 on root 2 here. This is the first time it's actually at the base angle, pi on 4. We're going to go all the way around the unit circle. I have to wait all the way to here until we generate it for the second time. So if this is 8 pi on 4, which is 2 pi, this value here is going to be 7 pi on 4. All right, so they're the 2 times it's going to do it between 0 and 2 pi. So I'm going to start writing out these solutions. So I'm going to say that 2 alpha, now notice that what I'm solving for here is 2 alpha, okay, equals, and I'm just going to go forward here. You'll see in a sec why I'm going to start writing solutions down here. So this is pi on 4 and 7 pi on 4. All right, now what we're going to do is just read what this 2 alpha means, or this 2 alpha means. So in terms of transformations, this is a dilation factor half from y. Okay, and remember dilations from y change the period. So what this is going to do is actually make it do 2 cycles of cosine in 2 pi. So if I was to do this graphically, right, here's 2 pi here. All right, we're going to get 1 cycle of cosine and then a second cycle of cosine to 2 pi. What that means is 1 on root 2, which is this positive value somewhere up here, is going to intersect once, twice, 3, 4 times. There's going to be 4 positive solutions between 0 and 2 pi. So what I'm going to do is generate some more solutions. I'm going to keep going around again. So I'm going to go from 0 to 2 pi and then another 0 to 2 pi. Okay, so I'm going to go around again. So here I'm at 8 pi on 4. Now I'm going to go here, which is actually another pi on 4 plus 8 pi on 4. We're at 9 pi on 4. Now the other way you can do this is look at this value here and simply add 2 pi to it. Okay, and 2 pi is 8 pi on 4 plus that is 9 pi on 4. So we could do that with this one, add 8 pi on 4 to this one here, and that would be 7 plus 8 is 15. Or we could note that this would be 4 pi here. 4 pi take away pi on 4 would be 15 pi on 4. Okay, so we've got our 4 positive solutions. Okay, now you might be thinking, well, that's out of domain because this is much, much further than 2 pi. But remember, I know that these solutions are now or are soon going to be dilated by a factor of a half. So that's why I've generated them, and when I dilate it, this will bring them back into the domain. Okay, so now I need to go from 0 to negative 2 pi as well. Okay, so I'm going to start here and I'm actually going to work my way backwards now as well. Okay, so I'm going to generate these solutions backwards, okay, because it basically is saying not just the positive solutions, we're going to continue this backwards to negative 2 pi. All right, so it's going to generate 1, 2, 3, 4 solutions for the negative values of x. All right, so the first one is generated if I go 0 and back pi on 4. I'm going to go negative pi on 4. That's going to be all the way down to here, which is negative 7 pi on 4. Then we're going to go all the way around. You can see that all that's happening here is that we're negating these values here. So it's 7 pi on 4, negative 7 pi on 4. So the next one's going to be negative 9 pi on 4 and negative 15 pi on 4. Now that doesn't always happen. That's going to be something that's going to be unique to cosine in this case. I'm just going to make a little bit more space for me. myself. So cosine 2 alpha equals negative 9 pi on 4 and negative 15 pi on 4 equals. Alright, so we've got our solutions. Now, other mistake I've made, that shouldn't be cosine, that should just be 2 alpha. So 2 alpha equals these values here. Okay, so I shouldn't have written the cosine there, don't know why I did that. Up here, notice that when I solved this one here, I just wrote down theta equals. Okay, so now we've got 2 alpha equals all of these. Now we don't want to solve for 2 alpha, we want to solve for alpha. So that means that what we've got to do is dilate all of these by a factor of a half or divide them by 2. So that's going to be negative 15 pi on 8, negative 9 pi on 8, negative 7 pi on 8. Okay, and we can see that 16 pi on 8 would be 2 pi, so we've hit the max part of the domain here, I'm pretty sure of that, and we've also hit the minimum part of that domain there. So we've got all of our solutions right here. Okay? Alright, so give that a practice. There's many problems to practice there in 6E. Okay, so give all of them a good go and see how you go. There's heaps and heaps of videos out there of teachers teaching how to solve trig functions. So if you didn't like this one, suggest you go on, have a look at, Eddie Wu or anyone else like that who's solved a trig function, and you might find something useful or something explained in a certain way in their videos. So good luck with that, guys.